I'll explain the concept of space charge region in PN junction with a simple teaching aid. For more videos on semiconductor devices, the working principles of transistors and diodes, etc., and on VLSI, subscribe to this channel and don't forget to like this video and click on the bell icon for getting updates. Here we go. So in this video we'll try to understand the PN junction diode space charge region. PN junction space charge region or depletion region. Okay, so here I have drawn a diagram, a slab of semiconductor. There is a red line here. So right side to this red line is N-type semiconductor, left side is P-type semiconductor. So we have we can see different cycles here: green cycles, red cycles, black cycles. So green cycles are silicon atoms. So this is a silicon atom. So this is also silicon. Silicon. All these green circles are silicon. And red circles are trivalent atoms. Say for example they are boron atoms. They are boron. And similarly, so we have black circles here to the right side. They are, say, phosphorus atoms. When the silicon is doped with foreign atoms, it becomes extrinsic silicon. So right side is when it is doped with pentavalent atoms like phosphorus, it becomes N-type, and the left side is doped with boron atoms, trivalent atoms, it is becoming P-type semiconductor. So this is P-type, this is N-type. So they are it is a single slab. So when it is coming close to each other, when P and N-type are coming close to each other, or when P is formed in N-type semiconductor, so then what is happening at the junction? Okay, so let us try to understand that. So in the N side, we can see that they are pentavalent, means this is a phosphorus atom is having 5 valence electrons. So it is bonded with 4 adjacent silicon atoms. So 4 electrons are shared with the silicon atom electrons, valence electrons, and 1 extra electron is there. And similarly, this phosphorus atom is having 1 extra electron, and this also having 1 extra electron. In the P side, we have the boron atoms doped. So it is a trivalent, that means it is only having 3 valence electrons, and all 3 are sharing the valence electrons with the neighboring silicon atoms, and 1 is having not sharing an electron. So there is a vacancy over there. So with this vacancy, it is neutral actually. When this vacancy is filled with an electron, it becomes negatively charged. Similarly, here there is a vacancy here. Okay, there are 3 extra electrons here. There are 3 less vacancies in this side. So what will happen when they come close to each other? There are more electrons in the right side here in the N-type and less electrons in the N side. So there is a tendency of the electrons to flow from right side to the left side. So that's called diffusion of carriers. So when there is a charge gradient, so there is a tendency of flow of the charge from higher concentration to the lower concentration, which is called the diffusion current. So these electrons will tend to move from right to the left. So for example, say this electron can easily be freed. This 5th electron of the phosphorus atom can be easily freed, and it will move from right to the left. Why? Because there is a concentration gradient. There is more electrons here, less electrons this left side. So it will come here and it will fill the gap of the boron atom here. So what happens when it is leaving its parent atom and coming to this the left side? when it is leaving the electron here, this phosphorus atom, which was neutral with 5 electrons, will now become positively charged because it has lost 1 electron. It becomes positively charged. So when this boron atom has received the electron, and this becomes negatively charged or negative ion. So these ions are immobile charges, or it is called the space charge. Okay, so that they cannot move. These ions cannot move in the material. They won't move, but they are charged particles. Okay, so because of this immobile charge, there builds up an electric field from the positive charge to the negative charge. There is an electric field. Okay, so the field direction is from positive to the negative. So there is an electric field here. Alright, so another thing happens simultaneously. When there is an electric field, this electric field will attract the charge carriers, the mobile charge carriers. So the electrons will be attracted from left to right due to this built-in electric field. So there may be simultaneously some bonds may be breaking in this due to the temperature. So for example, this bond is broken and created an electron. So this electron will be tend to move from left to right due to the presence of electric field. So it will move from left to right. It will come from there to here. Okay, it will remain here. So simultaneously, due to the gradient of concentration, this electron also may come from here and fill this gap here, making this negative immobile ionic charge, and this phosphorus atom is positively charged ion. So there is electric field again. So the electric field is getting increased. So thereby it is attracting the electrons from left to right again. They are moving from right to left due to diffusion, and they are moving from left to right due to electric field. So this bond may be breaking, and this will try to move from left to the right. So the movement of electrons due to the presence of electric field is called the drift current. The movement of electrons, charge carriers, due to the concentration gradient is called the diffusion current. So the diffusion current has to be balanced with the drift current. Okay, so the drift current now has to be balanced with the diffusion current. So at any moment of time, the total charge, the charge neutrality, when there is no external power supply or the bias supply to this, the charge neutrality has to be maintained in the semiconductor. Either the charge neutrality condition, the drift current and diffusion current will be remaining same. So there are 2 electrons moved from right to left, filling these holes, and the 2 electrons which are created due to thermal generation, they moved from left to right due to the presence of electric field. So there is no continuous movement of these electrons from right to left, because as they are moving from right to left, they are leaving behind an immobile ionic charge, which is called the space charge, which is developing an electric field. The electric field will keep on developing up to the level where the diffusion current is now balanced with the drift current. So at this particular moment of time, the diffusion current is now balanced with the drift current. So the net current has to be 0. There is no net current through this slab because there is no applied potential across this external potential. So due to this built-in immobile ionic charge, there exists an electric field, and that electric field, when you solve the Poisson's equation, that gives to a potential. When you integrate that gives a potential that's called the built-in potential. So that's called the built-in potential of the PN junction. Okay, so this is called the space charge. So up to here, this is called the space charge. This is a negative charge. So this is positive charge. So the positive charge and negative charge, that forms the depletion charge, that is also called as a space charge region of PN junction diode. Okay, so the drift current and diffusion current have to be equal. So the electric potential will keep on developing up to a particular level until it balances the diffusion current, which is due to the concentration gradient. So that's a concept of space charge region and built-in potential in PN junction diode. We'll see in the next videos more videos on the PN junction when it is reverse biased and forward biased, and how it acts as a rectifier and the working principle of a PN junction diode. See you in the next video.